Hi, and welcome back again. In the previous video, you learned how to compute double integrals over rectangular regions. However, most regions you encounter are not rectangular. So you want to increase the number of regions over which we can compute double integrals. In this video, we will discuss two such types of regions, which cover a wide variety of useful regions, such as parallelograms, circles, and triangles. We call them type 1 and type 2. But this terminology is not standard, so you might encounter different terminology in your calculus book. A type 1 region, or y-simple region, is a region where the y-coordinate is bounded from below by a function g1 of x and from above by a function g2 of x. In such a region, x is in between two numbers a and b. A typical example of a type 1 region can be seen on the screen. A type 2 region, or x-simple region, on the other hand, is a region where the x-coordinate is bounded from the left by a function h1 of y and from the right by a function h2 of y, while y is in between two numbers c and d. Again, a typical example of a type 2 region can be seen on the screen. A region can be both type 1 as well as type 2, only type 1, only type 2, or neither type 1 nor type 2. For each of these cases, you can see an example on the screen. So why is it interesting to look at regions of type 1 and type 2? Well, it turns out that you can express double integrals over these regions as iterated integrals, just as we did for rectangular regions in the previous video. Let's take a look at what happens. Consider the following solid, which is the region below the graph of a function defined on a triangular domain. This triangular domain is of both type 1 and type 2, but for now we'll treat it as a type 1 region. Our goal is to compute the volume of the solid, which is the double integral of the corresponding function. We cut this region up into slices with width delta x, just like we did when we first considered rectangular regions. Let's take a closer look at such a slice. So how would you compute its volume? Well, since the slice is very thin, we can assume that the variable x is more or less constant within the slice. As such, the volume of the slice is given by the thickness of the slice, delta x, times the surface area of the side view. As this area is the area below the graph of the function, this area is given by the integral of f over the variable y. However, what should we take as the limits for this integral? Well, since the domain is given by the triangular region, we should only consider those values of y that are featured in this particular slice. The lower limit for y is always given by 0. But if you take a look at the picture on the right, you see that the upper limit for y depends on which slice we consider, so it will depend on x. Since the formula for the upper line of the triangle is given by y equals 2 minus 2x, this means that the upper limit for y in the integral should be 2 minus 2x. So if we compute the volume of a slice, you see that for each value of x, we get different limits in the integral. So the limits of the integral are functions of x themselves. Now, in order to find the total volume of the solid, we should put all slices together, which means that we should integrate over the variable x. We end up with an iterated integral where we first integrate y with limits that may depend on x, and then over x with limits that are constant. In general, this means that we have the following result. Suppose D is a type 1 region with x in between a and b, and y in between g1 of x and g2 of x, then the double integral of a function f over this region D can be expressed as an iterated integral where you first integrate y from g1 of x to g2 of x, and then you integrate x from a to b. It is important to notice that the limits of the inner integral can now depend on x, while the limits of the outer integral still have to be numbers. This makes sense if you remember that the outcome of the double integral should always be a number and cannot depend on x and y anymore. The procedure for integrating a function over type 2 region is similar. Here, you always integrate over x first, and use h1 of y and h2 of y as the limits of the inner integral, then you integrate over y from c to d. So what would be a general procedure to compute a double integral? The first step is always to sketch the domain D, as it helps you to visualize the situation. Based on this sketch, you can then determine whether it's a type 1 or type 2 region or both. In the third step, you write the region D in the relevant form matching the type you just determined. And the final step is to write the double integral as an iterated integral, which you can then proceed to compute. Let us take a look how this works out in a concrete example. Consider the triangular region D with vertices 0, 0, 0, 2, and 2, 2. The first step is to sketch the region, and you see the result on the screen. Then we claim that this is a region of both type 1 and of type 2. So let's see why this is the case. For good measure, we will write it down in both forms. As a type 1 region, we note that y is bounded below by the oblique line y equals x, and y is bounded above by the horizontal line y is 2. In addition, x runs from 0 to 2. As a type 2 region, we find that x is bounded from the left by the vertical line x equals 0, and from the right by the oblique line x equals y. Here y runs from 0 to 2. Now suppose we want to integrate the function 2 times cosine y squared over this region D. Let us first try to compute it as an iterated integral, treating D as a region of type 1. Then we end up with the integral you see on the screen. However, the inner integral is very hard to compute by hand. So maybe it helps to treat D as a region of type 2 instead. In that case, the double integral becomes the one you see on the screen. The function is constant as a function of x, so the inner integral can be computed easily. The resulting integral might seem intimidating at first, but it can actually be solved quickly by substituting u equals y squared. This leads to the final outcome, which is the sine of 4. Now you know what a type 1 and type 2 region is, and how you can compute a double integral over such a region. See you next time.